Okay, so I think it's recording now. So do you guys have any questions? Okay, so last time we talked a little bit about kind of so we did the Chinese remainder theorem, and then we talked a little bit about algebra and geometry and how these two concepts go together. So algebra, geometry. So let me first of all, don't burn my back. Okay. So so last time, go a little bit bigger. So there was so we kind of made this this statement that a lot of what we're doing right now is really secretly a lot about geometry. So we have so geometry. So this is like scheme theory. This is what algebraic geometry studies, and then there's commutative algebra. I guess. Yeah. What the heck? It's stopping for some reason. Let me. Let's see. Okay, maybe it's going now. Okay, so we had some comments, some things that corresponded here to each other. So, so one of the things that we had was we had this notion of irreducible component. This was corresponded to a prime ideal. So a minimal prime ideal. Of I. So like here, this is what we could call V of I. And so like you could have two things, and this could be x, y is equal to 0. And then, you know, this thing here, this corresponds to the fact that I is equal to x intersect y. And here I is the ideal generated by x, y. Okay. Then we had so connected components. And so this had to do with idempotence. So these are E such that E is equal to E squared. And then you could take a ring here, A, and you could write your ring as AE direct sum A 1 minus E. Okay, and so here, I don't want to do this anymore. Go away. Other.
Can I ask about the minimal part?
Yeah.
The generated by x times y and the intersection of x and y, there's a possible proper containment if they're not reduced, right?
Or
minimal.
So sorry, I don't know what is going on here. Oh, so I think I closed this. If they're not what did you say if they're not reduced?
Yeah, so you got this ideal I, right? And
yeah.
It might have nilpotent elements. You're trying to get rid of them or something, or what do you say?
I could in general have nilpotent elements. To get rid of nilpotent elements, that's a different thing.
Okay.
So that's the one down here. So here it's like as two pieces. Sorry. You know, you have the union of two things, right? But idempotence, or sorry, nilpotent elements. Sorry, this should be on the other side. Right, so this is infinitesimals. infinitesimal, you know, information around your variety, your scheme. Let me say scheme. Okay, so what do I mean by this? So a nilpotent element is one such, so this is some f in the ring A, such that f to the n is equal to 0 for some n, and greater than or equal to 1. Okay, and so the idea was like you could have, so here, okay, so this, we can look at a ring here. So here I'm drawing spec of A mod I, right? So this is spec of A mod I, and here A looks like, or I, let's say A looks like, well, A is C adjoint XY, and I is the ideal XY squared, right? So so here, so then there was like killing the infinitesimal information, which was taking radicals, right? So taking radicals. So this is, you know, I goes to, you know, the radical of I. So this is killing infinitesimal information. Okay, and so like the point is here, if in this running example, so the radical of I is just equal to xy. You know, and if I is equal to xy squared. Okay, so it goes back to this example here where there's like no infinitesimal information. And I don't know if we talked about other, I think this is pretty much what we talked about. And so extra components, right? So you can detect whether or not there's extra components by the existence of zero divisors, right? Your scheme has either multiple components or, you know, multiple components up to multiplicity. And that's the same thing as infinitesimal information. Okay, so
when we say up to multiplicity.
So what do I mean to up to multiplicity? I mean that, like, okay, so what's the difference between this one and this one, right? These two ideals, right? The difference between these two ideals is this one cuts out the x-axis and the y-axis, the union of the x-axis and the y-axis. This one kind of cuts out the y-axis twice, or the x-axis twice, right? So it's prescribing a higher order of vanishing, right, than just vanishing with multiplicity 1. It says that if you have a function, so to be a member of this ideal, you have to vanish with multiplicity 2 for the y part, right? And that's why we draw this as thicker. So really, like, having infinitesimal, so like if your quotient ring has infinitesimals, right? So this is the quotient ring. This is infinitesimal nilpotent elements in the ring A mod I. Okay, so and so, like, I guess in this side we're talking about the ring A, it's properties of the ring A and quotients. Okay, well, let me do it like this. There's so this is V of I, subset of spec of A. This thing is the same thing as spec of A mod I. Okay, and then there's this quotient. So you have then you have, instead of an inclusion here, right? So this thing here, this inclusion. Oh, dang it. This inclusion here, dang it. Okay, this inclusion here corresponds to this quotient map here. Okay, so so idempotence could be, so it depends on what you're talking about. So this is idempotence of so let's say idempotence of, maybe I should have written it like this to keep everything consistent. A mod I E direct sum A mod I 1 minus E. And then this is this thing what I'm drawing here is spec of A mod I. It's got 2 points. And so here you could have something like C of XY, sorry. So let's actually, let's do A, C of X and I. This could be like X minus 1, X minus 2. And then this could just be the line, right? And then you have 2 components here. You have the point at 1 and then the point at 2. Okay, sorry, what was your question again? I think I feel like I got off track there.
Oops, I'm muted. Didn't realize that. There's like this thing. This is like a piece of language that I'm not entirely used to in mathematics, where we say like up to something. So like down below, we said that these schemes are has multiple components and up to
multiplicity. So that means like, so what I was saying is that you'll have well, how do I make this more precise? So if there's no zero divisors, right, then that means that you're not going to have, all I'm saying is that if you have no zero divisors, then you're not going to have so if there's no zero divisors in A mod I, so this means that spec of A mod I, which is the same thing as V of I, right? This thing will have will be one connected component. Will be one component, and there's no infinitesimal information. No infinitesimal. Ticketing. Okay, I need to tell you guys something and come clean on something. Okay, so so here I'm going to tell you something a little bit more information. Okay, maybe we'll help you out with this. Okay, so before I defined spec of A, so when I said that this was a collection of prime ideals. Of A. Okay, and then we put with the topological space structure. Okay, so it's a set plus a collection of open sets. This is not quite true. This is a little bit of a lie. Okay, the true story is that I'm going to do this. This thing here is really 2 things. It consists of an underlying topological space and a sheaf. So this is a topological space. And this is what's called a sheaf of rings. Okay, okay, so it is true that, and so this topological space is the collection of prime ideals of A, right? A ring A, and this thing here says. So what does this thing do? So for every open set, every U, which is an open set of spec A, right? O spec A of U is a ring. This is some ring that we construct. Okay, I'm not going to get so much into the details here, but what I want to say is that I've been calling this thing, what I've been calling spec A is really just the underlying topological space of the scheme, right? And so, okay, so now I need to tell you something else. So here's a theorem. So this thing contains, okay, so let me say the kind of the idea here, the big idea is that, like, okay, so this, well, okay, let me just say the theorem. The theorem is that, so for any ring A, and any ideal I in here, I in A, we have that spec of A mod I as a topological space is equal to spec of A mod the radical of I. Okay, so in particular, like this thing here, so recall that that this thing here is equal to without fuzz. Okay, so okay, so this one is like the full picture. And then this thing here is just the topological space information. So the topological space information does not care about radicals of ideals, right? And so what we're doing here in commutative algebra is we're secretly dealing with this kind of more weird part of what a scheme is, which is this sheaf of rings. And this is so it's like we have a topological space, and then we have this thing that kind of keeps track of extra information about the ring, about the ring, which is like the infinitesimal information. And eventually this whole theory gets built up so that you build up the theory of schemes where you don't just have this spec thing, but you have kind of like in manifolds, how things are locally like Rn, we build up spaces that locally look like this, that locally look like affine schemes, and affine schemes are this thing. Okay, all right. So that's kind of a mouthful, right? But okay, and I kind of want to say a little bit more about the radical. Okay, so let me try and say some more about the radical right now. We'll come back to this throughout the semester, and hopefully it'll become more clear as you guys work with it a little bit more. Okay, so one of the things that I want to do is I want to prove the following. So let A be a ring, and let I be an ideal in the ring A. So one thing that I want to prove is I want to prove that the radical of I is equal to the intersection of prime ideals okay, so now I'm going to do the topological space thing, and maybe I'll go change the notation everywhere. to do this thing. So you put an absolute value around spec A to denote that we're only working with this topological space, right? Of P containing I. Of P containing I. Okay, so I want to show this. And what is this? Okay, so what does this thing do? So the idea is that you have, so this ideal here cuts out, it's like a system of equations, okay? And what these things are these are the irreducible components of this. So many times, okay, so let me make a remark. Often, the intersection is finite, like in a Noetherian ring, is finite. And you have this thing here. The radical I looks like P1, intersect P2, intersect blah, 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 intersect PR. Okay? And so what is this? The geometric meaning of this is the following. So you'll have V of I, and V of I will look like, you know, it'll look like something like this. Right? And so V of I is the union of the prime ideals above it. Okay, so these things here, the prime ideals in this intersection here. So if we want to show that the radical of I is the intersection of all the prime ideals above it. So these things correspond to the primes here correspond to irreducible components, and that's what we're doing. Is geometrically, when we want to decompose this thing, we need to find the irreducible components, and this thing allows us to find the irreducible components. Okay.
Primes don't have nilpotents either, right?
Primes do not have nilpotents, no. A prime ideal is by definition radical. A radical ideal is one which is its own radical. Okay. And so, okay, so let's talk about how to prove this. Okay. So to prove this, let's do the following. So let's do a lemma. And this is kind of the hard part of the theorem. So let A be a ring. Okay, so the radical, so this is what's called the nilpotent radical. This is the nilpotent radical. It's all that, this is the collection of all nilpotents. Of all nilpotent elements. Okay. So this is just going to be the intersection of all prime ideals. Okay, so this is the lemma that we have. So notice this is, okay, so what is this thing? So this is the set of all f in A, such that f to the n is equal to 0 for some n greater than or equal to 1. Okay, so it turns out that all the nilpotent elements are, it's the radical of the 0 ideal, because the radical of the ideal is all the things that f to the n is in some power of the ideal. And it turns out that's intersection of all prime ideals. Okay, this theorem is going to imply this theorem. This is the theorem we care about. So this is the big theorem. This is a big theorem. For us, this is a big theorem. Let me just say that this is a big deal. Okay. And we're going to get at this thing from this. Okay. So let's do the proof of the lemma here. Okay. So let's do the first thing. Let's show that this thing here is contained in the intersection of all prime ideals. Oh, okay. Sorry. I'm going to abusively write. I should be doing this every time because we're doing the topological space. And really, the spec A has a little bit more information than just that. But I might abusively just write spec A and omit the sheaf of rings. All right. I shouldn't, yeah, don't focus on that part. It'll just be, yeah. I just wanted to say that it's more than just a topological space, this thing. So on the other side, it's really like the ring, right? The ring contains all the information about the geometry, and we could recast it into this other thing called a scheme, but it's really just rings. Rings are really about geometry. Okay. All right. So if okay, so let's do this. So the base case. Okay, so what we're gonna show, if f to the n is equal to 0 and p is prime, then f is an element of p. Okay, and so we're gonna do induction on n. So if n is equal to 1, then f is equal to 0, which is in P. So every ideal contains the 0 element, because you can just multiply elements times 0 and it's in there. Okay, so let's do the inductive step. Okay, so we'll suppose f to the n minus 1 is equal to 0 implies that f is in P. Okay. Okay. Now suppose. So this is the hypothesis here. Assume this in our proof. Okay. Now if f to the n is in P, then we have the following: f to the n minus 1 times f is in P. Since P is a prime ideal, this implies that f to the n minus 1 is in P, or f is in P. Well, okay, and this completes the proof, right? So by inductive hypothesis, if f to the n minus 1 is in P, then f is in P. And if f is in P, well, then f is in P, right? So it's kind of tautological, right? So we handled the two cases. Okay, so now we need to show the hard part. Okay, so here's what we did. We were showing this thing, so that the radical, the nil radical, right, is contained in the intersection of all prime ideals. So now we need to show the converse. Okay, we need to show that the intersection of all prime ideals, right, for P and spec A. So this is contained in the nil radical. Okay, so we need to show the other way around. Okay, and so for this we need to show a trick. So we need to do something backwards. Okay, so I'm going to do like a little aside here. Okay, so I'm going to do something that's kind of a little bit strange. I mean, so we're going to do the contrapositive. Okay, so this thing here. Okay, let's just suppose that x is a subset of y. Right? So you need to show that x, an element of x, this is the same thing as x is an element of x implies that x is an element of, let's say a is an element of x implies that a is an element of y. So this is the same thing as, so this statement here is the same thing as a not an element of y implies a not an element of x. Okay, so what we're going to show is we're going to show that if f is not nilpotent, so this is saying f is not nilpotent, then there exists a prime in the a prime ideal. So there exists a prime ideal such that that F is not in the prime ideal. Okay. Notice the reverse of this is saying that if F is in every prime ideal, right, then F is in the nil radical, right? So like if you negate this, right? So let me just do it like this. So this is the statement that we're going to prove. Oh. And notice, I just want to make a little point out about negation, right? So if I do negation of this thing, if I do the negation of the whole thing, let's see, or let's see, actually, let's do the contrapositive of the whole thing. So all I want to say about the negation of this is that so to flip quantifiers to negate a statement like this, you flip the quantifier and then flip the statement. Okay, so this would say for all P in this thing, F is an element of P, right? So this thing is equivalent to, so this whole thing is equivalent to, for all P spec A, P, F is an element of P, implies F is an element of the radical. Okay, so this is the negation of this statement, this is the negation of this statement, and I just flip them. So when you flip statements with quantifier, you just flip the quantifiers and flip the statement. Okay, anyway, so this is what we're going to prove. We're going to prove this one.
Taylor,
Yeah.
can we just kind of go like, can we just get recentered on what's the big goal that we're trying to prove right now?
To prove that the nilpotent radical is the intersection of all prime ideals.
Okay.
Okay, we proved one inclusion that the nilpotent radical was contained in the intersection of all prime ideals.
Okay.
Now we need to show the other way, that the intersection of all prime ideals is contained in the nilpotent radical.
So if we have a thing that's in all of these things, it's in this nilpotent radical.
Exactly. That would be this statement here. If we have something, if we have an F that's in all of these, then it should be in here. But I'm going to prove the contrapositive, that if F is not in the nilpotent radical, then there exists a prime ideal such that F is not in the prime ideal.
Got it.
Okay? And so if I were to just do that right away, I think that it's like, what are you doing? At least that's what it looked like to me. It looked a little weird. Okay, yeah. So I'm going to explain how this proof goes.
Cool.
Okay?
Yeah, I was just trying to make sure that I had the lay of the land, as it were.
Yeah. Okay, so this proof is going to use the axiom of choice. Okay, so suppose F, so we're doing this like the same sort of trick when we constructed a maximal ideal. Suppose F is not nilpotent. Okay, consider the set S, which is the set of all powers f to the n for n greater than or equal to 1. Right? Okay, and then we consider the collection of ideals. The collection of ideals not contain. So I'm gonna what I'm gonna do is I'm gonna construct a prime ideal, right? So we're supposing F is not nilpotent, which is here. I'm gonna construct a prime ideal that doesn't contain F. Okay, that's the goal, right? So we're considering the collection of ideals not containing S. Okay, so so in particular, this is non-empty. Let's call this set of ideals sigma. Okay, so sigma is not empty since the zero ideal is in sigma. Okay, so the zero ideal doesn't contain this because this is exactly the hypothesis. This is exactly the hypothesis that F is not nilpotent.
Zero is not in S though, right?
Zero is not in S. Zero is not in S, and it's not in sigma. Right? S is
Zero
yeah.
is
If zero was an element of S, then F would be nilpotent.
0 is an element of sigma.
The zero ideal is an element of sigma, not the zero element.
Okay, because yeah, sigma has a non-trivial it doesn't intersect S everywhere. Yeah, right.
Exactly, it doesn't intersect X. Exactly, that's correct. Okay, so all right, so my claim. Okay, so now by the axiom of choice, or Zorn's lemma, right? There exists a maximal element ideal of sigma. So by a maximal ideal, let's say maximal element of sigma. Let's call it I. Okay, it doesn't have to be a maximal ideal. It's just an ideal, right? It's an ideal which is maximal with respect to the property of not containing the set S. Okay, so the claim that now what I'm going to show is the claim I is prime. Okay, and so this will be the prime ideal. So note that this is the prime ideal that we wanted to construct. This is the prime ideal, not containing F. That proves the theorem. Okay, so let's do the proof. Oh, I'm going to do something else weird. Okay, so second weird thing I'm going to do. Okay, second weird thing. I'm going to do contrapositive again. Okay, so we have, so the condition that P is prime. This is if and only if, right, xy is an element of P. I'm sorry, xy is an element of P. Implies x is an element of P or y is an element of P. And this is equivalent to the contrapositive, right? X is not an element of P, and y is not an element of P, implies xy is not an element of P. Okay, so I'm going to prove this. I'm going to use this statement. Okay, so let's do the proof. So suppose x and y are not elements of I. Okay, then x plus I and y plus I are not in the collection sigma by maximality of I with respect to this property.
When you add ideals, it always gets bigger, right?
Yep, when you add ideals, they always get bigger or stay the same, right? Depending what you're adding by. Okay, so this implies, one, that there exists an n, a natural number, such that f to the n is in x plus I, and there exists some m, a natural number, such that f to the m is in y plus I. Okay, this is what it means to not be an element of sigma, right? It means that it's going to intersect that set S somewhere. Okay, so this implies that f to the n plus m is not an element, is an element of, well, if I multiply these two ideals, I plus x, I plus y, and this thing here is I plus xy. Okay, how do you see this? You just distribute them out. If you distribute them out, well, you'll see that I times y and I times x, those are just contained in I. Okay, so you can check that one. Okay, convince yourself of that. Okay, And so then this implies, this implies that I need to erase that. Okay. So this implies that I plus xy is not an element of sigma. So in particular, xy is not an element of P. Okay, so this is an ideal that's strictly bigger. This ideal here is strictly bigger. Oh, sorry, not P, I. I called it I. I don't know why I called it P. I. Okay, I is P. Okay, so xy is not an element of I. If xy were an element of I, right, this thing would be still contained in this collection, right? But it's not in the collection, right, because of this property. It contains some power. So we just proved that it's prime. And so the side, this shows I is prime. Is prime. Huh? All right.
That was the contrapositive of being prime. X, Y, and I means either one of them, as you said, suppose that they're both not. Okay,
Yeah.
that's right.
We're using this statement here. We used
yeah.
We're using this thing here. You know, we used here, here. Right? Suppose that x and y are not in there. So x and y are not in there, then that implied that xy is in there. And we showed that it's a prime ideal. I mean, so that shows it's not a prime ideal, and it doesn't contain f. Okay. And so that proves, you know, again, by this contrapositivity, right, that this containment. Oh. Okay. All right. So let me continue with what we want to do now. Okay. So so now let's continue with this theorem. So let's prove a lemma. So so now what I want to do is I want to prove two things. Okay. So I want to prove the main theorem. So the proof of the main theorem needs two more lemmas. But the main idea is that we're going to use the lattice isomorphism theorem. Okay. So we're going to use that the inverse image of ideals is ideals. Okay. So let me prove two lemmas. So to prove the theorem, we need two more things. And so this is kind of related to the exercise or the quiz that we had on Friday. Two more things. Okay, one, lemma one. Okay, so let A be a ring, and I an ideal of A. Okay, so let Q be the quotient map, be the map here from A to A mod I. Okay, so what the first claim is that the inverse image of the radical ideal of the quotient. Okay, so this is the so this is the radical ideal, the nil radical of the quotient ring. So this is the radical of I. So it's like you can so what it does is it converts the ring of nilpotent elements, or the collection of nilpotent elements in the quotient ring. If I take the inverse image of that, that's just the radical of the ideal, which was the kernel. Okay, so that's one of the ways that you can convert everything, all this business about radicals, into business about like nilpotent elements. Okay. The other thing that we have is that the lattice isomorphism theorem for ideals respects prime ideals. Okay, and what do I mean by that? Is that what I can do is I can take the topological space. It's actually even an isomorphism of topological spaces, but I just want this as lattices. So here, so this is the collection of prime ideals of A mod I, and this is a bijection. It's actually an isomorphism of lattices. So this is the set of P, which is a prime ideal of spec A, right? Such that P contains I. So there's a bijection between the set of prime ideals of your original ring and the spread of prime ideals of your quotient ring, right? And what it does is it takes a prime ideal here and it maps it to Q inverse of P bar. So this is a prime ideal. And so here, Q is the map from A to A mod I. Okay? Okay, so using these two facts, let me give you the proof based on the two facts. It's very quick. Lemmas. Okay, so what do we have? So we have that this nil radical here. So this was the big thing that we proved today. So this was the intersection of all prime ideals of the quotient, right? So this was P bar, right? Then we just take we just apply Q inverse to this equation. Q inverse to this equation, where Q is the quotient map. Okay, so lemma 1 takes care of the left-hand side. Lemma 1 says, so this is lemma 1. This is lemma 2. Lemma 1 tells us that this thing. So this is my way of saying this is the zero ideal in this ring. That's what the subscript means. So this is the radical of I. Lemma 2 says that this thing here of this intersection if I take this thing, so this is just the intersection of prime ideals in this ring that contain I. Right? And so this gives us so these two things are equal, right? Because you can take Q inverse of both sides of an equation, and then you get this. Okay? This one we're going to do as an exercise. So this is already an exercise. And then maybe I'll do this one next time. Okay, sorry for running 2 minutes over.
Taylor, is not that first lemma almost just by definition, or I might be missing like it?
It's almost by definition, yeah. So
Yeah,
I mean, if you look at T. M. McDonald, they don't even make any remarks on this.
Yeah. Looking
yeah.
at the Wikipedia page, it's like almost just like that's like what it has to be if you just read the definition of the radical ideal.
Yeah. I mean, that's what you do. So you just write down what they are, and then you show that they're equal, right?
Okay.
So I wrote like a little half a page or a page of it,
Okay.
But it's it's not. I mean, it's very doable. It's but you should just check it,
Yeah. Okay.
Yeah. Just make sure you convince yourself that it's true.
Taylor, on the lemma 1.
Yes.
Okay. On lemma 1, what is that? After you do the squiggly, it says something of quotient. Is that supposed to be nilpotent?
Nilpotent. Oh, nil radical.
Okay. That makes more
So
sense.
nilpotent radical is the nil radical.
Thanks.
So yeah, sorry. All right, so I'm going to stop the recording.